Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about the factors that affect the rate of a chemical reaction. Our aim for today is how can we qualitatively describe the four factors that affect reaction rate. There are four factors that affect the rate of a reaction: temperature, concentration, particle size, which is also surface area, and the usage of a catalyst. The first factor is temperature. Generally, temperature and reaction rate are directly related. That means when you increase the temperature, you are going to speed up the rate of the reaction. Whereas when you decrease the temperature, you are going to slow down the rate of the reaction. The reason for that is when you increase temperature, the particles move faster. And the faster the particles move, the more likely they are going to collide. Remember, for a chemical reaction to take place, you need an effective collision. An effective collision occurs when particles collide with proper speed and orientation. By increasing the temperature, you're speeding up the particles, and with that greater speed, they are more likely to collide, resulting in an effective collision. What we have here are two flasks. The one on the left is the cold temperature, measuring about 6 degrees Celsius, and the one on the right is the hot temperature, measuring about 88 degrees Celsius. We also have two balloons, one blue for cold, one red for hot, and two Alka-Seltzer tablets. I am going to take the Alka-Seltzer tablets, break them into pieces, and put them in each of the balloons. Then I'll put the balloons over the mouth of the flask. Let's see what happens when I lift up the balloon, pouring the Alka-Seltzer into the water. As you can see, the red balloon, the hot temperature, is blowing up, is inflating much more rapidly than the cold temperature. Remember, increasing the temperature will also speed up the rate of reaction. The second factor is concentration. Concentration and reaction rate are also directly related. As you can see, we have two containers of equal volume. The container on the left has more particles, which means it's a higher concentration, than the container on the right, which has less particles, which means it has a lower concentration. The container on the left will have a greater rate of reaction because there are more particles crammed in the same space, which means when they're moving around, there will be more collisions. The more effective collisions we have, that means we have more chemical reactions. So the container on the left will have an increased rate of reaction. For the next demonstration, what we have here are two plastic water bottles and two concentrations of hydrogen peroxide, H2O2. The one on the left is 3% hydrogen peroxide, and the one on the right is 30% hydrogen peroxide. So for this next demonstration, we will test how concentration affects the rate of reaction. I will pour equal amounts of hydrogen peroxide into each of the water bottles. Remember, the left one is 3% hydrogen peroxide. On the right, we have 30% hydrogen peroxide. Next, we are going to add manganese dioxide. We'll add just the tip of the scupula and see what happens. A little fizzing, not much. Now let's test the 30% hydrogen peroxide. not only was there fizzing, but there was vapor that left the top of the plastic water bottle, and the water bottle actually shrunk. To the touch, the water bottle is hot. As you can see, the water bottle on the left, which contains the 3% hydrogen peroxide, looks normal, whereas the water bottle on the right, which contains the 30% hydrogen peroxide, has shrunk. The third factor is particle size, or surface area. How do they relate? Well, if we had two containers with equal masses of reactants, but the container on the left has fewer, bigger particles than the container on the right, which has more, smaller particles, the container on the left has a smaller surface area, whereas the container on the right has a greater surface area. The container on the left will have a lesser rate of reaction because there are fewer particles to collide. The container on the right will have a greater rate of reaction because there are more particles to collide. Remember, in order for a chemical reaction to take place, you need an effective collision with proper speed and orientation. So, an increase in surface area increases the amount of reactant exposed for the reaction. This increases the collision frequency and the reaction rate. How can you increase surface area? Well, you can dissolve the solid reactant in a solution, or you can grind the solid into a fine powder. The smaller the particles are, the greater the surface area it has. For this last demonstration, we will test to see how surface area affects the rate of reaction. For this demo, I will need a Bunsen burner, a metal scoopula, a watch glass, and some lycopodium powder. I will take the scoopula and scoop some lycopodium powder onto the center of the watch glass. I will then light the Bunsen burner. When you light a Bunsen burner flame, you always strike the match away from your body first before you turn the valve on, and then light from the side. As you can see in the flame, there are two cones, the hotter inner cone and the cooler outer cone. What I'm going to do next is I'm going to take the Bunsen burner, turn it upside down, and place the flame into the lycopodium powder. Lycopodium powder caught fire, but didn't really react too much. However, if I take the lycopodium powder and I throw it into the flame, you see there is a greater rate of reaction. Why? Because when I throw the lycopodium powder into the Bunsen burner flame, the lycopodium powder spreads out, more surface area. That way, more of the flame can interact, can react with the lycopodium powder, causing a greater, a faster, and increased rate of reaction. And the fourth factor is the use of a catalyst. A catalyst is a substance that increases the rate of reaction without being used up during the reaction. This is important. While a catalyst can be added to a chemical reaction, it's neither a reactant nor a product. Actually, when you would write a chemical reaction, a chemical equation, you would put the catalyst on top of the arrow. Since a catalyst is not used up during a chemical reaction, it could be used over and over and over again in subsequent chemical reactions. A catalyst, how does it work? It allows reactions to proceed along a lower energy path. On the Regents, you might see a multiple choice question stating that a catalyst provides an alternative energy pathway. What does that mean? Well, if we had just a regular potential energy diagram, a catalyst is not going to affect the reactants or the products. Just this hump in the middle So a catalyst is only going to affect the activation energy. Before, without a catalyst, if it required this much energy to initiate reaction, to activate the reaction, now the catalyzed reaction only requires this much energy to activate, to initiate the reaction. So the activation energy barrier is lower for a catalyzed reaction, which means with a lower activation energy barrier, more reactants have the energy to form products. More reactants can become products at a given time frame. So, as we said before, since catalysts are not consumed during a chemical reaction, it does not appear as a reactant or a product. Instead, a catalyst is often written above the yield arrow. So this is a common equation I'm sure you've seen before. 6 carbon dioxides plus 6 waters goes to yields 1 glucose and 6 oxygen molecules. This is the equation for photosynthesis. Photosynthesis, photo meaning light, synthesis to make, using light to make food. However, the light is not a reactant or a product. It's a catalyst, so we write it on top of the arrow. Finally, if we're talking about a biological catalyst, that is known as an enzyme. An enzyme is a specific type of catalyst. It has to be a biological catalyst. Like in your mouth, when you digest starches into sugars, in your saliva, you have an enzyme called salivary amylase. It speeds up the reaction in the breakdown, the decomposition of starches into sugars for digestion. Please take out your chemistry reference table and open up to Table I. Heats of reaction at 101.3 kPa and 298 Kelvin on page 5. Table I is arranged in this way. The first 6 reactions are combustion reactions. You have a hydrocarbon plus oxygen gives off CO2 and H2O. The next 12 reactions are synthesis reactions. That goes from 2CO gas plus O2 goes to 2CO2 gas, all the way down to H2 plus I2 goes to 2HI. These are all synthesis reactions, which means putting 2 smaller things together to make one bigger thing. So here you'll see all these synthesis reactions have 2 reactants and 1 product. The next 6 reactions are a little bit different. You'll notice that there's an ionic compound in the reactant side. Then on the arrow, on top of the arrow, you'll see H2O. All of these ionic compounds are being dissolved in water and dissociating, breaking up into their cations and anions. So all these are dissolving or dissociating in water. The final one, H plus OH minus, goes to H2O. That is a neutralization reaction. When you add an acid to a base, they neutralize each other. They get closer to a pH of 7. That's what's happening down here. We'll learn more about that in the next unit. However, the most important thing about Table I is this little asterisk down here at the bottom, which corresponds up here. The asterisk reads, a delta H change in heat values are based on molar quantities represented in the equations. Okay, the important part is here. A minus sign indicates an exothermic reaction. So when you look at the delta H values, if there's a negative sign, it's an exothermic reaction. most of these reactions are exothermic. There are some endothermic reactions. An endothermic reaction would be represented by a positive sign. So, for example, if I was to take down here ammonium chloride, NH4Cl, and dissolve it in water, and it breaks up into NH4 plus and Cl minus, that is an endothermic reaction. That is going to feel cold to me because it's taking in heat. That's the reaction used in ice packs. Let's take a look at this worksheet. For problem number 1, we are going to rewrite the equations with the heat of reaction on the correct side of the equation. Now this reaction, CH4 gas plus 2O2 gas goes to CO2 gas plus H2O liquid. That is the very first reaction on table I. So what we're going to do is we're going to rewrite it, putting the heat, the kilojoules, on the right side. When you look at table I, you see that the heat of reaction for this first problem is negative 890.4 kilojoules. Since it's a negative sign, that means this reaction is exothermic and the reaction is losing heat. So when we rewrite the reaction, we are going to put the heat on the right side. It is being lost. It is coming out on the product side. So remember that number, 890.4. When we rewrite this, CH4 gas plus 2O2 gas yields goes to CO2 gas plus 2H2O liquid plus 890.4 kilojoules. When the heat is on the right side of the arrow, when it's in the product side, I know that it is an exothermic reaction. However, on the next one, N2 plus O2 goes to 2NO gas. That is a little bit farther down table I. That is right here. So we see that this reaction, N2 gas plus O2 gas, goes to 2NO gas. That is a positive 182.6, which means this is an endothermic reaction. So when we rewrite our equation, we must put the heat on the left side, on the reactant side. So we rewrite it, N2 gas plus O2 gas plus 182.6 kilojoules yields 2NO gas. The heat energy is on the left side. It is going into the reaction, which tells me the reaction is absorbing heat, therefore it is an endothermic reaction. Please do problems 1C, D, and E. Now, let's look at question 6. Question 6 states, given the balanced equation, 4Fe solid plus 3O2 gas goes to 2Fe2O3 solid plus 1640 kilojoules. Which phrase best describes this reaction? Well, when I look at the energy, the 1,640 kilojoules is on the right side of the arrow. So automatically I am thinking exothermic. So I could get rid of choice D and choice A. Now I'm left with two choices, either positive 1,640 kilojoules or negative 1,640 kilojoules. But remember what table I tells us. That asterisk tells us a minus sign indicates an exothermic reaction. So if it's truly exothermic, it can't be positive 1,640 kilojoules. It must be negative 1,640 40 kilojoules. So the correct answer is C. Problem number 7 is one of the trickier problems that the Regents could ask us. Problem number 7 states, given the reaction, 2H2 gas plus O2 gas yields 2H2O liquid plus 571.6 kilojoules. What is the approximate delta H value for the formation of 1 mole of H2O liquid? This equation gives us the delta H for 2 moles of H2O liquid created. For this problem, I only want to know the delta H for 1 mole of H2O created. So what I must do is divide the number of kilojoules by 2. Here I'm making 2, but I only want to make 1, so I must cut the energy in half. When I do that, I get 285.8 kilojoules. So now I know the correct answer cannot be C or D because it has to be 285.8. I just cut it in half. Finally, is it positive or negative? Well, once again, since the energy is on the right side of the arrow, the right side of the reaction, it's a product, it's on the product side, that means this value must be negative. So my correct answer is choice A, negative 285.8 kilojoules. Similarly, question number 9 states, based on reference table I, when 2.00 moles of NaOH solid dissolves in water, then it gives us some choices. Well, let's first take a look at table I and NaOH dissolving in water. Remember, the dissolving in water is towards the bottom of table I, and here, NaOH, 1 mole of NaOH dissolving in water will give off 44.51 kilojoules. Remember, that's for 1 mole of NaOH. But question number 9 is asking us for 2 moles of NaOH. So what we must do is we must double this number. So negative 44.51, if we double that, that's going to give us negative 89.02 kilojoules. So that gives us either B or C. We can get rid of choice A or D. Now let's read them both. B says 89 kilojoules of energy is absorbed and the temperature of the water decreases. And C says 89 kilojoules of energy is released and the temperature of the water increases. Remember, this minus sign states that is an exothermic reaction. So energy will be released in the exothermic reaction, and therefore the temperature of the water will increase. The answer is choice C. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about kinetics, collision theory, endothermic versus exothermic chemical reactions, and how to read table I of the chemistry reference table. I hope you learned something today. Please join us again soon. Have a good day.